Good morning, everybody. I will first of all also say thanks to ESJU company based in middle part of Finland in Oulu, which provides some, let's say, idea for this talk, and especially so the cut data there I'm going to show. Well, wind turbine generators has usually are now quite common on highway, but they are even played somehow on sea and so on. And it's a kind of EMC problem that we have when they are maybe hitting by lightning strike, is that we have a quite large platform, let's say, with very small details to be somehow resolved. Kilometers of cables inside, and each of these cables or this bundle can have plenty of really thin wires or complex coaxial cable and so on. So we are therefore trying to solve a multi-scale problem, which I will try to somehow explain in another way. So what we need to do is like to have a lens or somehow a satellite which is able to resolve for a very far distance. What you see here, maybe you can recognize, is the River Rhine, which is not far away from Darmstadt. But you need to have such a lens that zooming and zooming is able somehow to, let's say, resolve the CST building, which is not actually where we are, it's just next, so the blue tower. So this is the kind of problem that, let's say, CST STUDIO SUITE, the tool that I'm using, needs to resolve if we want to make, let's say, an example. How we can solve this kind of problem? Well, first of all, we need a transient solver, since for a general electromagnetic environmental effect, they are all in the time domain, so like the lightning analysis. We have seen the presence of plenty of cable inside, and I will introduce you a hybrid meter that CST software use in order to simulate 3D environment with very detailed cables. And we need to consider that most of the cables and other electronics inside, they have termination on circuit elements. So therefore, we need to couple a 3D electromagnetic field, which is basically the tools that we are using, with a circuit simulation. When starting a modeling a lightning problem, the first, let's say, question you have to answer is, what kind of channel I would like to, or what kind of strikes I would like to model? We can consider a couple of two effects. We can have a near strike or direct strike, and for that, CST STUDIO provides different kind of sources. We might first start with a plane wave, which could be a nice first approximation of a near strike. A second, maybe a bit more detailed, is the use a thin wire with impressed transient current inside to simulate, let's say, a near strike. So here, the, let's say, devices under test is not our WTG is not represented, but the most dangerous and let's say the example I will show is based on that is a direct strike, which needs to be, let's say, simulated, take into account the complete current path, the complete channel. This is the example where a lightning is somehow striking on the sphere, on the edge of the sphere. A second point is to characterize the waveform. We have seen that by, let's say, standard waveform is definitely a double exponential, The value that we have here, 88 microseconds and 1.5, are the most common. And we have already discussed that we might easily represent that with a double exponential. CST tools, they provide a library of different signals, and the double exponential is one of them. You can maybe even import ASCII tables, so if your signal is coming from measurement and so on. We have seen that already commented, so it's not quite critical from the, let's say, frequency range point of view, so we can still consider low frequency, especially if you are coming from, let's say, RF world, where maybe already a few gigahertz are considered low frequency. But we have seen a lot of shapes of lightning, and maybe the double exponential is not sufficient anymore. So that's why CST provides a nice VBA editor on which you can really describe any kind of waveform that you have. In this case, we want to simulate a double subsequent strike, and what you see here is actually the function. They are just two commands. So I would say 5 variables and 2 lines which describe this signal. So therefore, the library is already implemented for the double exponential, but if you want to have a general waveform, so you can easily describe by VBA command. On wind turbine generator, the lightning strike is somehow hitting, in this example, so a large dimension structure. We are above or even more than 100 meters. And if we see inside here, so we zoom in the engine part, so we might have complex details of the engines, and we have some internal cables and so on. But if we zoom, for example, on the soil, where the tower is grounded, we have other elements like some RLC elements that need to be modeled. And don't forget that we have to somehow describe all the feedings and all the grounding lines, which can be easily done by wires. What are the features that we use for that? We have seen all the simulation I have performed on this wind turbine generator are done it by the transient solver, so based on finite integration technique. And the transient solver supports high-performance computing to simulate a large number of mesh cells in a very short time or relatively short time. We have seen that the engine has a quite complex and detailed information to be captured. So that's why the finite integration technique is quite suitable, since we support a technology called perfect boundary approximation. I'll show you what that means. Extremely important is the models of the materials that you can have. So especially for the frequency-dependent materials. When representing feeding and grounding, we might use so-called 3D wires without really describing the cylinder of the dimension, which is quite straightforward to be implemented. And then, since we want to consider the cabling, especially signal cabling, which are controlling the electronic part, so I'm not talking anymore about, let's say, feeds or grounding, which, let's say, can be easily represented by a wire. But if you have cable bundles and so on, you might need to integrate the finite integration technique or the transient solver with a dedicated tool for studying cables. So, and I will show you how I applied this tool for the WTG. The technique to accelerate the simulation are different. So you might have multi-threading, so multi-CPU and so on, but I think this is quite straightforward now. And we might have GPU computing, or you can have distributed computing or MPI, what is called, let's say, clustering and so on. For this kind of simulation, I've used the GPU computing since, let's say, it's most likely the most efficient way to speed up. GPU is actually a graphical processor unit, so it's a graphic card that you can easily plug in your computer or have it, let's say, in external rack outside. Actually, the simulation is not running anymore on the CPU, but it's running on this GPU. We support at this stage the NVIDIA Tesla card, mainly two series, the 10 and the 20. And on the, let's say, on the left-hand side corner, or up corner, sorry, so we see the performance, how fast could be a simulation, a typical simulation, or the speed up, if you compare with a normal Intel, or it's not a normal, but it's already one of the latest Nehalem CPU. So you can see that if you have one of these GPU, you can speed up to a factor of, let's say, 6 to 8. It depends, of course, by the dimension. So not 6 to 8%, 6 to 8 times faster. So let's say 600% faster. If you double the number of GPU, you can go up to 10 and even 16, 15. This is, of course, dependent by the problem. We can see that here on the, we compare even how large the problem that I solve can be accelerated by the GPU. Here I have the million of mesh cells. With one GPU, you can easily go roughly a bit of 50 million, more than 50 million mesh nodes. And with two, you are about 100, 120, and you can go up to, let's say, 250 million or a bit less with 4 GPUs. Here, I compare with a series called 10, which is, I would say, the old one. So it's coming a new series called 20. And on the top on that, so we have done already some comparison. So let's say on the top of, let's say, 6, done it with Tesla, so we can have a bit more, so another factor of 3 of speed up. So therefore, we can easily reduce by, let's say, 1 week to 1 day the simulation time, or from 10 hours to 2 or 3 hours easily the simulation time. Another way to reduce the number of mesh cells is to use the CST PBA technique. What we see here is the detailed part of the engine where a lot of curved parts and small detail are designed. And if we compare with the classical star case mesh, we might need to refine a lot, especially to avoid short circuits or to avoid, let's say, unwanted gap. This is what, in this case, so with a PBA, we can easily reduce the number of mesh cells that we need and keep the time step larger. When opening the material properties, you can easily find a lot of parameters to be defined. Let's say the most easy way to define a frequency-dependent material is to define the tangent delta. But this could be not enough. That's why we have a dispersion model that you can choose. Or if you go to user, you can easily load a frequency, a list of points where you have measured the epsilon. And what we do a fitting of this point to have a broadband model of that. So the fitting is done by an order. So it's a polynomial based on pole and zeros. And you can easily decide how many, let's say, polynomial you need in order to easily fit your curve. And the 3D wire are usually represented by very thin, let's say, can be easily designed by a curve. And, well, in this case, I assume that I use the lightning wire, especially for two purposes. First one is to characterize the lightning channel, which is up to me, so to decide which channel is actually the lightning taking. And so we suppose that the lightning is striking the edge of one sphere, and then I have to consider the exit wire. So I consider that from here some of the ground line are designed. I have connected them to the ground as well. The wires are used to represent feedings and groundings and so on. At this stage, so still I don't want to characterize electronics, cables, control cables, and so on. So therefore, this is a pure 3D field, electromagnetic field simulation. And well, what kind of data we can have? So we are actually able to monitor to a specific point a current going through some lamp elements, and to plot both time domain response and the frequency domain response. So you can maybe move to a bit more critical, let's say, measurements. So the each H field and E field as well. So here we'll just plot H field probes. So actually we can place probes in the air and or in the dielectric and try to measure how much, how big is the H field or E field at that point. So this can be done both in time domain and frequency domain as well. And then, of course, a critical, let's say, a big advantage of the simulation is that you can really see the field, where the field is propagating. Of course, this gives you the possibility to produce nice pictures or nice movie, but maybe let's go a step forward. If we try to localize on the details, a time domain field, like in this case, so here we see the lightning strike from 0 to 150 microseconds roughly, can easily help you to understand the coupling mechanism. So how the field is coupled into your device under test, or how the field is coupled into the wire or other point. So this is an extremely useful features of every, let's say, 3D electromagnetic tools, but especially for the time domain, it's really describing what's happening there. Next step is to integrate the, let's say, the harness cable. I suppose that there is a control cable which is somehow connecting the control PCB placed here nearby the engines to the axle of the steerer. We can define now a bundle of different cable inside. So what you see here in dark blue is not anymore, let's say, a 3D wire, but this is representing a route where my cable harness is lying. Inside this cable harness, I have different cables. In this case, I choose a twisted pair. So we provide a library of cable that you can easily extend. So we have a twisted pair here. Usually red means that is a conductor, and green are representing dielectric materials, and the blue one is usually a ground, or in this case, for this cable, which is a coaxial cable, is representing the outer conductor. So when introducing cables in this kind of complex structure, so we are now introducing a concept of system-level simulation. Therefore, it becomes interesting to define how the system is coupled. And I take mainly two definitions. Could be a weakly coupled system. So therefore, an S-parameter simulation, so putting in cascade, or a spice simulation putting in cascade would be enough. But if you have a strongly coupled, like in this case, you might need other techniques, like the hybrid method, which I'm going to show. And don't forget the circuit elements available, which might require, again, a co-simulation between 3D electromagnetic field and circuit. So when using the cable studio, you define the route, quite straightforward. So you start from a wire, from a curve, and you define a route. Then on this route, so you can lie cable, and you get here the number of you see, you will have two different single wire cables. We have a coaxial cable, G58, and we have a differential path. Cable Studio starts and resolves the cables with a 2D transmission line technique. And here we visualize the meshing. So actually the cable is sliced in different parts. And what we see here is the different TLN segments. Here as a point, we have still the cable. Is actually this one. So you see how small it is in comparison with the size. And this blue line, they are representing the ground. This segment here, it's roughly, I think this is segment 4. It's representing this part, maybe with a rounded object nearby. And this is the segment 2. I think we are here, this part of cable. And what we see here, the circle around, is representing this metallic part. If I zoom here, I get again my cable harness. Now I have to decide how to couple my cables to the 3D field, or to the 3D simulation. So what I have three possibilities to coupling to 3D. This means coupling to 3D EM field simulator. Well, maybe the first and easiest ways to do is to have no coupling. So I select none, and well, at the end, I have here my cable studio block, which is just representing S parameters, or it's just representing a SPICE network. Since I have no coupling defined with the 3D, I have to define the coupling by myself. So this is what we call a coupling via S matrix, if we consider the system weakly coupled. So we just have a coupling on the terminal. It's a very straight way to really put together 3D structures and cable and so on. It's actually used to for closer structures. It works quite well, but has the disadvantage that I couple only between the two terminals, and I neglect any radiation into cable. And of course, so if I have really strong radiating element like antennas inside, or this could lead to a limited accuracy. A step forward is to consider a coupling between the cable and the 3D via electromagnetic fields. So what I do, I consider the field around the cable, just consider nearby the cable itself, and then in the 3D, I consider an equivalent source. So the advantage is that I, let's say, monitor the electric field and H and E fields around the cable, and when running then the 3D, I don't need to simulate all the small details of the cable itself. So this is what we call coupling via 3D fields interface, and has many advantages already, since you can use different techniques to couple, and but still, let's say, radiation is partially taken into account, and it works, let's say, just one step in one direction. So if you have the back radiation into the field, into the cable, you need some iteration to be simulated. So that's why what we strongly recommend to do with the cable is a so-called co-simulation or hybrid cable-to-field method. So with a hybrid cable-to-field method, actually we substitute the field, the cable with the field. We can have a unidirectional coupling, or we can have a bidirectional coupling. If we have a back radiation from the cable, so the cable is the victim, and it's somehow back radiating, you might need to go to the bidirectional. But if you have a lightning, it's really unlikely that a lightning strike has a back radiation coming from something. So therefore, or especially a cable, it cannot disturb the lightning itself. That's why I use, or I choose as a method, a unidirectional. Together with that, I can perform a transient analysis which consider exactly the excitation, since I'm working in the time domain, exactly for every time step. So this is the setup. I go to unidirectional, and immediately the cable is intelligent enough to find the closest ground, since the cable was still, let's say, lying in the air, and automatically try to close itself on the ground, since we need a closed path for the current. So we have it here as a detail, and here it's connected to this piece of metal. Then I have again my block with some termination. These grounds and resistors here are representing the termination of the signal. And as you can see, I don't have any excitation here, since this is an irradiation problem, so I don't need to feed the external. So the irradiation is coming from the 3D. So here I will go fast through the, let's say, features, but I hope you can easily require or have your contact partner, so at CST, to test the 2011 release, which supports all these new features. So you can decide which kind of solvers you want to use. You can even consider the TLM. I use the transient solver for that. And the type of simulation, radiation from cables or irradiation into cables. So I choose the second one, since we decide to have just a unidirectional coupling. Of course, if I choose a bidirectional, it doesn't make sense to choose between radiation and irradiation anymore, because they are both taken into account. When setting the task, can be frequency domain task or time domain, and you don't have to set any excitation again. So leave it empty. And automatically, after some hours of simulation time, and I let it run it not less than one night. So otherwise, I could not produce any, let's say, results for today. But this is the, let's say, the maximum time that you might simulate, especially at the beginning. So what we here immediately recognize, it could be that around 20 gigahertz, there is a strong resonances. This is the 3D with the coupling approach. If we go back to the slide, with the S matrix, we see that the coupling is more or less low. So there is not really any point or any frequency which is more critical than the other one. Instead, when considering the field coupling or the hybrid method, clearly, let's say around 20 megahertz, we might have some problem. Well, these are all kind of information that you can get from an electromagnetic tools. Then now it's up to you to check why this is coming, maybe just putting monitors around that frequency, and especially how to fix the problem if this is a problem, or try to avoid to have devices working at 20 megahertz. the benefits of a 3D electromagnetic simulation are different, but I will summarize on three. Well, the first one, I think we have always to write to justify the investment that you do in the software. So you minimize the number of tests, especially for lightning, so it's not quite easy to reproduce it. So therefore, you have cost reduction if you use our product. But from a technical point of view, a 3D electromagnetic software really helps you to understand the coupling mechanism. So why such effects are, why my PCB is not working, or why due to a lightning strike, such part of the composite material is melting down. So this is actually what you can really see and understand with a 3D electromagnetic software. It would be extremely difficult that on such a complex system like a wind turbine generators or even an airplane, you have a measurement and you have done some simulation on radiated field, and the two overlap each other. I think there are too many unknowns somehow that it's become quite difficult to really have overlapping measurement and simulation. But what you can really estimate with electromagnetic simulation tools is that if you apply a fix, so you have understand your problem, you have to understand your coupling mechanism, and you apply a fix. You shield the cables, you put some EMI filters and so on, you will get some benefits. This can be easily estimated, this kind of benefits, by such a tool. So, thank you for your attention. Any questions?
Okay, thank you, Diego. So